Hello, I'm Vasant Nanjandeshwan, Senior Director of Product Management for Automotive Cockpit Solutions at Qualcomm Technologies. I'd like to take this opportunity to thank you for joining me today at Lenaro Connect. Today, we'll look a little bit deeper into the new trends in the digital cockpit designs and how Qualcomm is addressing this changing landscape. The automotive industry is at the inflection point of a major change and evolution to the electrical engineering architecture. These changes have significant impact on the overall evolution of the next generation of cockpit designs and significant changes in the platforms required to support them. And the end customer can look forward to some game-changing technological trends. I'll try to provide an overview of the new changes that are coming in and how Qualcomm plans to address them. Consumer, specifically mobile technology, has had a profound impact on every one of our lives in the last decade. It has transformed the way we communicate, work, and consume data. It has also accelerated the onset of several new technological progress and changes in many industries with far-reaching consequences beyond just the mobile industry. The automotive industry is also a victim to those major changes, and in the last few years and in this coming decade, will clearly be driven by huge changes in the very architecture of the car electronics. Users are now addicted to consuming data on demand, being connected with each other through social networking, and more importantly, having the devices or products be attuned to their needs. And personalizations driven by advances in AI machine learning are obviously driving innovation in the auto space as well. Connectivity and on-device intelligence are catalyzing unprecedented transformation in the automotive design and changing the way automakers think about cars and services that customers want. We've seen the growth of an entire industry based on shared car ownership, similar to Uber and Lyft, and now the next few years will belong to driving the autonomous experience. Now, all these technologies are anchored by advances in mobile communications, primarily 5G, C-V2X, to name a few. And Qualcomm is at the forefront of all these new technologies and pioneering advances in these domains: 5G, C-V2X, digital cockpits, autonomous driving, and the connected car based on car-to-cloud services. Today, we'll focus on the cockpit of the future. So, what can one expect the cockpit in the car of the future to look like? Well, one hope it is close to resembling the picture shown here: an amalgam of information needed for operating along with autonomous, semi-autonomous driving and the comfort of streaming media consumption. The push towards autonomous driving would imply the need for driving data to be presented and consumed differently from today. It needs to be a seamless blend of safety and comfort. With the onset of high-resolution displays, one can imagine the car of the future to feature a plethora of displays and cameras, including high-resolution clusters, the main information or infotainment console, passenger or rear seat displays. I could support a gaming console-like experience. Side and rear view mirrors are totally replaced by camera-based feed warning of cars, obstacles in the drive path. The drivers and the passengers would interact through edge-based digital assistants, providing the necessary personalization for each passenger in the car. A basic extension of your living room to the car: comfort, safety, entertainment on your commute to work, school, road trips, etc. But to deliver this digital cockpit of the future, there are many changes needed in the way these systems are designed in the car today. The future is palpable, but need a few finishing touches to get there. But before that, let's look at a little bit of history and a blast from the past. If one were to move the clocks back about 20 years, the unique selling proposition of a car entertainment was perhaps a 5-inch dash screen that would support some form of 3D graphics, a huge improvement from the 2D LCD screens that would read out album art or information on screen. I remember my first IVI system was a removable panel that was rage in the early 2000s. But then a decade later, thanks to the growing compute and convergence of communications, we've kicked off the onset of a connected car with many displays. It's still a far cry from the cars of today, but clearly a huge change from the basic audio-video systems of the early 2000s. And then we started to see the push for higher performance, safety, computer vision advances that precipitated a consolidation of different displays and domains. And that brings us to the cars of today. It supports state-of-the-art displays, clusters, audio, video, along with personal assistants with the latest in automotive OSs. So one can see how the changes in the E architecture will push us to the car of the future that we saw before. The progress is steady, continuous, and it's built on the backbone of high-performance silicon. It's similar to the ones that Qualcomm produces in this market. So how does auto differ from the mobile or consumer user experience? Well, the way we interact with the system is very different to begin with. We have many screens, many audio zones, with many camera inputs coming in at any time. This is coupled with stringent mechanical and quality requirements that the cars need. Well, there's common grounds in terms of compute, graphics, and AI power that the mobile chips and the auto chips deliver. There's a clear dichotomy in terms of performance, power, and thermal needs of a car. There's a higher integration needed with every generation of designs, and customers expect a seamless experience switching from their phones to their IVI systems. With every generation of our cockpit solutions, we've provided a high-performance, highly integrated cockpit platform of our future for our customers. The Snapdragon cockpit solutions are designed to provide this innovation, deliver a rich multimedia, including premium content streaming, multitude of displays, camera integration, audio zones, with engine sound cancellation or enhancements and personalized sound bubbles. With the integration of heavy compute, machine learning, GPU display foundational IPs, and heavy AI accelerators in the software framework, the user is provided a safe, protected, and distraction-free experience in the car, while the rest of the passengers can enjoy a media-rich journey. Qualcomm was in the forefront of the innovation from a single screen to multiple screens, and our platforms are designed to drive the confluence of compute, comfort, and consolidation in the car. We looked at the past, now let's look into the future. There are three major trends that drive the evolution of the car architecture: macro automotive trends and micro trends that are specific to cockpit and ADAS architectures. Macro auto trends include the drive to electrification, the growth of autonomous driving, the ever-increasing ramp of connected cars, and lastly, the shared car experience. All these trends are mileposts in the march towards the software-defined car of the future, one that provides dynamic configuration of the car and pushes the transformation of a mechanical, hardware-centric vehicle to a software device on wheels. We've already seen such a transformation with some leading car makers across the globe. EVs and connected cars will be the majority of the cars that are sold in the next half of this decade. While we could argue about how truly autonomous or self-driving cars could be, we're clearly down the path of more autonomy than less. The macro trends, in turn, influence the ADAS and cockpit domain architectures. The ADAS domain complexity rises as we move from level 2 to level 5, thereby necessitating the need for higher perception, cameras, radars, and other sensors. Similarly, the complexity in the cockpit domain is also increasing. High-resolution displays, streaming media content to occupant displays, in-car monitoring service, all of these contribute to the growing complexity in the cockpit domain. Together, these micro and macro trends drive the adoption of a new EE architecture, what's called the zonal compute architecture. So what are the changes in store for the EE architecture? We're already in the midst of this transformation from a decentralized architecture to a domain or a zone-based design. The underlying devices, semiconductors, will need to provide high-performance compute blocks, GPU, CPU, machine learning, etc., coupled with a new service-oriented software architecture. Let's take a look at this new EE architecture and the changes that are coming in. The current architectures can also be termed as traditional or a central gateway-driven architecture. There are modular designs with multiple 50 to 100 ECUs, embedded control units, in a car, each with a specific function. As an example, you could look at the battery management ECUs, environmental or control ECUs, each of them interfacing with the vehicle gateway. Now, this central gateway is slowly being replaced by the domain controller, and these domain controllers consolidate the functions of multiple ECUs. A perfect example of this is the current generation of cockpit domain controllers, which seamlessly mix the functionality of IVI, cluster, heads-up display, rear seat, audio processing functions into one ECU, and that interacts with the vehicle backbone, which is in the form of a CAN or some form of Ethernet-based backbone. The domain controller is now commonplace due to the inherent advantages of lowered cost because of ECU consolidation, reduced cabling and weight costs, and leveraging the advantages of silicon innovations, thereby providing the optimum performance-power trade-off. But it has its limitations in addressing the growing complexity of the ADAS and cockpit domains. The software complexity is also growing, and the AE architecture needs to evolve to a more centralized compute or zonal architecture. This zonal architecture is defined by the need for a homogeneous compute solution that allows for the reuse of hardware and software resources, and the zone controller has the information for a specific zone. For example, cameras or radars are then shared with the central computer. The key benefits of this new zonal architecture is the reduced complexity of the compute domain, reduced costs due to the consolidation of domains into one controller, and then reducing the cabling costs. This reduced complexity and cost are the primary driver in the adoption of the new zonal architectural trends. Now, we can clearly see the automakers' motivation in adopting the new zonal architecture. Now, let's take a closer look at the components in this architecture. The main building block is the central computer that provides consolidation of cockpit, ADAS, gateway controllers, body controller ECUs, telematics, and wireless ECUs, among others. Now, this central compute ECU will be paired with satellite ECUs or aggregators in the zones that provide legacy support. The central compute ECU will integrate high-speed serial links called SerDes or new Ethernet topologies, including time-sensitive real-time networks, to connect to the zones and provide the multi-tens of gigabits of Ethernet or bandwidth that's needed for real-time communication support. The zones would in turn connect to the external displays, cameras, audio, video sources, and high-speed actuators and sensors, including LiDAR or imaging radar. In the software side of things, the paradigm also shifts to real-time oriented hypervisors. Increased security, as well as legacy code application support would be needed. And additionally, this safety separation is needed for the aggregation of these various domains. Scalability is a key challenge, and we need to meet the price expectations of every tiers of cars without compromising on safety. So how does one scale the zonal design? Well, one approach is to use a blade-like design, similar to the high-performance compute cluster used in servers and data centers. Each of these blades would comprise of homogeneous compute SoCs that can then serve as multi-purpose SoCs, either as an ADAS device or an IVI device or a fused function. These can then scale the performances desired and provide the redundant compute resources to provide further aggregation. The pictured modular zonal compute blade server is a step in the direction of the software-defined car. Now let's look at how Qualcomm plans to provide compute solutions to address this evolving landscape. To process the ever-increasing compute needs of the next generation, one needs an SoC that is designed with heterogeneous compute blocks that are specifically built to address certain functions and tasks. The SoC then transforms into a central hub for high-performance compute, computer vision, AI, or multi-sensor processing. The underlying solution needs to provide the compute horsepower needed for high concurrencies we saw before, but it also needs to process them efficiently and meets the power envelope that our car makers target. Power efficiency is gaining importance, especially in the era of EVs. Every watt of power consumed eats away at the range of EVs. Also remember that the car is a thermally constrained environment, so efficiency matters. Combining the many domains results in cost savings that the OEMs and the end customers can also benefit from. And last but not the least is the software infrastructure supported by our SoCs. They also feature a scalable and flexible software architecture that melds the functions and safety needs of the next generation cockpit, providing the separation for high performance latency, critical functions, and also providing the multimedia functions in another context. With its enhanced compute and processing capabilities, Qualcomm's digital cockpit platforms are now one of the most comprehensive solutions in the industry, designed to provide the best-in-class vehicle experience as well as safety, comfort, reliability, raising the bar for cockpit solutions in the industry. So what are the software building blocks of these platforms? Well, we continue the heterogeneous design methodology, which allows for specific blocks to provide dedicated functions and acceleration for specific functions. The integrated AI engine provides acceleration for machine learning or any computer vision use cases. It also provides any personalization needed for occupants, including natural language understanding, climate control, audio and personalization, and adaptive HMI concepts. We also have specific vision and perception accelerators, such as the Hexagon Computer Vision Accelerator. It combines the integrated ISP to provide the necessary camera processing capabilities, whether it's for in-cabin or around the car camera monitoring. These blocks provide independent acceleration for specific functions, while the integrated Cryo multi-core CPU subsystem provides high-performance command, control, and sequencing for all tasks. It also provides the virtualization support that's needed to isolate and separate safety-critical and non-safe applications. To serve the needs of a content-rich multimedia in the car, we've constructed our graphics, video, and display processing units to provide this functionality. Our GPUs provide the best-in-class power performance and are designed to deliver the best-in-class rendering engine for the next generation of wide, ultra-wide, or even panoramic displays. Then processed and then composited by an independent display engine. Premium streaming content can be decoded, decrypted, processed by our video and audio processing blocks. So you can see how this heterogeneous architecture provides the fabric for the multi-domain zonal architecture of the future. All these blocks are the backbone of the customer use cases in the car. Whether it's blending content from one screen to the other or providing voice-assisted navigation, our SoCs are built to process them efficiently and with minimum latency behind the scenes. Now let's look at the software support in our platforms. We provide a flexible, scalable software platform with comprehensive support for popular high-level operating systems, real-time OSs, and hypervisors to support virtualization and separation of the domains. Over the last few years, we've seen the adoption of cluster-integrated cockpit solutions. These are leading the industry in adoption of cockpit designs. While we see the hardware infrastructure and separation in our SoCs, we also provide the separation needed in software by coupling it with a hypervisor-based solution. All the critical functions that are essential to the safe operation, for example, rear-view cameras, round-view cameras, are all housed in the safety-critical partition. The infotainment content, which is typically less critical for the health and the safety of the car, would reside in the other domain. This allows us to provide a true smartphone-like immersive experience on one side, while providing the required separation for safety-critical applications on the other. This is a solution that we've honed over the last few years and are now providing to a number of OEMs. Now, one difference between the consumer space and the mobile space and the automotive space is the fragmentation of OSs. Most OEMs have assets in a certain configuration and have spent numerous years honing their code to meet their end requirements. To support such a diverse world of OSs, we need a framework that's fungible and provides the same sort of performance for any configuration chosen. Qualcomm does exactly that. Our integrated and validated software support the different hypervisor configurations, RTOSs, and OS configurations that our OEMs use. Now, additionally, we provide the separation that's needed for the safe domains and from the IVI OSs, either Linux or Android-based. We closely collaborate with our hardware and software partners, providing for a seamless experience, whatever the OS chosen, and we still have to adhere to the safety goals and key performance goals, such as early boot, instant on, etc. Now, you can see how our bespoke software development coupled with the hardware infrastructure and changes help to drive the cockpit designs of the future. Now, with the onset of global zonal compute designs and architectures, one can see the need to support many more virtual machines or VMs, perhaps additional safe contexts from a camera or other sensor inputs that the head unit receives. This is easily accommodated in our architecture, and the underlying architecture can be expanded to take on new functionality. Again, it's embedded by the underlying high-performance hardware design. So how does a developer like you get your hands on one of these platforms? Well, we have our auto development platform or reference platform for developers to try out. It's a self-contained system that will provide support for prototyping, reference for hardware and software leads, software development, integration, and testing for our partners. It'll also allow our partners, developers, and customers to work with various features and integration that we've been talking about before, including multi-display support, audio support, driver monitoring systems, etc. The BSP, the board support package, will include support for the hardware engines along with APIs for customers to take advantage of the underlying hardware. We'll also be providing software development kits for using our powerful AI and machine learning accelerators, advanced camera, computer vision, and imaging pipelines. The platform supports many pre-integrated and optimized middleware and BSP solutions, including driver monitoring, surround, and early rear-view camera, multi-mic, and multi-zone audio solutions. This is coupled with the support for the various HLOSs that our OEMs prefer to use. Now, we've addressed the performance and software and system design problems, but how about another pain point that customers face? The flexibility to upgrade features post-deployment. A big problem that any consumer faces today is the obsolescence of their system within a year or two of the purchase of the car. How does a system that is embedded keep up with the ever-changing landscape of content and applications that are prevalent in the market 2 to 3 years after the purchase of the car? Qualcomm's Car-to-Cloud platform solves this issue quite neatly. It provides the customer with the flexibility to start the production with a particular SKU or tier of performance. And based on the feature requirements, Qualcomm Car-to-Cloud allows for upgrades based on the performance needs. As we saw before, our SoCs are built with the best-in-class performance across a broad swath of IPs. And by provisioning for future performance in hardware and software, our Car-to-Cloud platform allows the system to scale up as needed. It's not limited to performance upgrades alone. One could upgrade on-demand features over the air, content, applications, and services such as Marketplace on the go. It provides our customers with the flexibility to start with a low investment upfront and then provides the option of improving performance in the field, almost like the consumer or mobile marketplace. I hope I was able to shed some light on our platform capabilities. From everyone here at Qualcomm, I want to thank you for spending your time with us today. Thank you.